This is the BLU meeting for August 20th, 2025. Our speaker is Ben Callis from Dartmouth. And Ben is a PhD, or did you get your PhD yet? Or are you just a PhD student?
A mere student.
Yep. And we're going to be talking about securing the Gnu C Library, which is the fundamental library that is used throughout Linux. Ben, you can start.
Okay. So let me get this up. For some context here, this whole effort came out of a course that I helped to run. That was about. It was basically we assembled some students to try to think about the glibc heap and go from not really understanding much about heap exploitation to trying to get to the state of the art on at least glibc, and then from there try to think about what can we do to improve where things are at. I would say it was a mixed success. It worked more or less. I mean, we got a lot of students to a point of doing pretty cool stuff. If I was going to offer it again, I would definitely change some things around. But to get started here, the assumption is that you're proficient with C. If you're not and you have questions, please just interrupt me. I'm not going to I don't really go over a lot of the details on the language here, but if something is unclear, please just interrupt me. We've got time. So then further, this class ran in the winter, and so some of this stuff is not 100% fresh in my mind. And just worst case scenario, if I can't remember a detail, I do have the glibc source right here, so we can always just pull that up and figure things out. So beginning with malloc, that's the memory allocator in libc, and so the interface here is you give it a size t, n, and it gives you back either a pointer to n bytes of memory that you can use for whatever you want, or null, usually indicating out of memory. And then free is the counterpart to malloc, and that's when you're done with some memory you got out of malloc, you just take that address that you got from malloc, you pass it back to free. And free, typically does one of two things. Either it's going to release that memory back to the OS, so if it was M-mapped, it'll M-unmap it, or it might keep that memory mapped and just keep it around in the address space to service a future call to malloc should that occur. Okay, and then glibc, as was said earlier, is kind of the standard libc for most Linux distributions. There's some outliers here, and there's certainly other libcs in use, but this is kind of the main one. And it provides the malloc that's used in most Linux systems. And this talk is really about malloc. Okay, so bins. Bins are kind of a key idea in the way that a glibc style allocator works. So the kind of the background here is you don't have to build an allocator this way. There's lots of allocators that don't work this way, but the glibc allocator is basically a huge pile of linked lists. It's all linked lists, and there are kind of different categories of linked lists, and each linked list is often referred to as a bin. So this when you hear bin, you should think linked list, and what goes on those linked lists, it's freed allocations. So you should think I make an allocation, I'm going to get some memory, I pass that memory back to free, and free either releases it back to the OS directly, in which case there's no more bookkeeping to be done, or free keeps it around to service a future call to malloc, in which case it needs to keep track of this allocation somehow. This freed memory needs to be stored somewhere so that it can later be used. And in glibc's allocator, that's in a linked list, and that's going to be inside of, the linked lists come in a few categories, and these linked lists are called bins. So the kind of first line of defense here, like you go to make an allocation, you malloc something, and where are we going to look first is in the T-cache. So T-cache is just a type of, there's many of these linked lists, and we're going to go through a lot of the different kinds of linked lists here. T-cache is just kind of the first one that gets checked. It's per thread. So when you go to make an allocation from the T-cache, you don't need to acquire a lock. So it's a lot faster than the other ways of making an allocation, the other places to store freed chunks. Okay, so T-cache bins, so T-cache linked lists store up to 7 small allocations. And asterisks on both of those things. First, you can have more than 7 things in a T-cache bin if you change a tunable. So this is an environment variable you can set to change the length of the max length of the T-cache bins. And what is meant by small here is smaller than some cutoff that's also tunable. So this is also something you can change. If I remember correctly, that second, the max T-cache size thing being tunable is like very recent, like in the last few weeks. So that won't make it to a release of glibc for a little bit of time. Okay, so when you free something, it goes into the T-cache if there's room and if it's small enough. If it's too large, it won't go in the T-cache. Yeah, so T-cache lists are singly linked, and each list stores allocations of a particular size. So within a T-cache linked list, every allocation is the same size. And chunks get inserted at the head of the list. Okay, so now let's show what that actually looks like. So here I have a tool that I wrote called Heap Explorer that is basically a little CLI for playing with the glibc heap and making allocations and freeing them and seeing what bins things end up in and what are the orders of these linked lists and whatnot. It's written in C. It works by parsing the heap out of memory. And the whole thing runs inside of a signal handler. So it can't call basically any libc functions. And so it makes a lot of raw system calls. It's not the prettiest code, but if you're interested, it is open source, and you can see it here. I can pull this up here. So this is the repository. You can LD preload it into an existing process, and then when you send Control-C to that process, it'll give you an inspectable and modifiable version of that process's heap. So you could, like, for example, run a Python interpreter with this LD preloaded, hit Control-C, and then, free half of the interpreter's allocations, and then resume execution and just see what it does. Like, this is the kind of thing you can do with this tool. But we're just going to use it to look at what the heap does kind of in a pretty standard scenario. So we want to know about T-cache. So let's just look, before we've done any allocations, what does the heap look like? And that's the for command here. You can see it's not the greatest user interface. So there's nothing. We've made no allocation, so there's nothing in the heap. And when it says this arena, when you hear arena, just think heap. Arena just means heap, basically. Every thread gets its own arena, but they're all locked, so they can all access each other's arenas. It's sort of complicated. All the stuff we're going to be doing in this talk is single-threaded, so really just arena and heap can be used interchangeably. So let's allocate a chunk, and let's say we get like 10 chunks that are all like 16 big. And then let's look at the heap. So this is what the heap looks like. And so we've got 12 chunks on the heap here. So the first is at this address, and it's a chunk of size hex 288. And that is the base chunk of the heap. When you make your first allocation, there's a bunch of metadata that needs to be stored somewhere that's like data about the heap. And it's actually stored on the heap. So among those things is actually the heads of the T-cache linked lists actually live inside of that base allocation. So before you've made any allocations, there just is no heap. But once you've made a single allocation, you actually get this extra allocation on top that just like is made by the heap initialization code that runs when you make your first allocation. So that's kind of the base chunk, and we're not going to be thinking about that too much for now. There are some techniques that make use of freeing the base chunk and then repurposing stuff that's there. And I don't really know too much about that, but I have heard interesting things in this direction. Okay, so here's our 10 allocations. We asked for 16 bytes. We got 24 bytes per allocation. And this kind of thing is pretty common. 24 is actually the smallest allocation size that glibc supports. So you make an allocation smaller than 24, even if it's 0, it's going to get rounded up to 24. One final note here is that the size here that I'm displaying is the size of the data, not the size of the overall chunk. So like there's metadata stored alongside the allocation that you make, and that's not included in this size. So this is 24 bytes of space for data that we got for each of our 16-byte requests. Okay, and then at the top, this is all I did was basically call malloc 10 times with argument 16 every time. I just said malloc 16 10 times in a row. So far, we've done nothing with that data. So it's just, we got 10 times 24 bytes of data on the heap, of like memory on the heap that we can use for whatever we want. Is that clear? Or is there a more fundamental question?
Oh, no, that's clear. Thank you.
Okay, cool. Thanks. Okay, so and then this chunk up here is the top chunk, and that is everything from like basically this is like a pseudo chunk that lives at the highest address on the heap and spans all the way to the end of the mapping for the heap. So when when I'm mallocing something, if we can't find a suitable existing free chunk to service this request, then we're gonna slice out some portion of the top chunk and return that from malloc instead. And if the top chunk eventually gets too small and we can't, the top chunk is no longer sufficient to satisfy a particular request, then either we'll burk or mmap or some other system call to ask the OS like, hey, I need more memory that can be used to get the user the amount of memory they asked for. Okay, so that's the 12 chunks that you get when you ask for 10 chunks. One is the top chunk, one is the base chunk, 10 chunks of what you want, but the size that you asked for could get rounded up. Finally, this size 24 might seem a little bit weird. It's really like arguably 32 because there's 8 bytes of metadata. So that's kind of where this comes from, so that the chunks can be aligned. Okay, so on to Tcache. Let's free some chunks. So if I free chunk 1, and then free chunk 2, and then free chunk 4, and then look at the heap, we can see chunks 1, 2, and 4 are in arena 0 because it's the main thread that allocated and freed them, and then Tcache is 0. So that means they're in the Tcache bin for the chunks of smallest size, which is 24. Okay, so let's look at that Tcache bin. If I say 5 and then print Tcache bin 0, we can see it looks like this. So first in the bin is F8, is this chunk at 5583C6F0B2F8. And that is actually the last one we freed. So here we see a property of the Tcache lists that should be familiar if you're familiar with like linked lists. Is like you got a singly linked list, you're inserting at the head. We're going to see these items in reverse order of how we inserted them. So this is chunk number 1, this is chunk number 2, and this is chunk number 4. And then, so if we print the heap, this is what it looks like now. If I malloc and I say, like, give me one chunk of size 1, and then I look what I got chunk 4. So we're just going to grab the first thing out of the Tcache that, fits. That's the first place we look when we go to malloc is check the Tcache. Is there something of the right size? If there is, return it. And so you can see we didn't have to go to the top chunk here or ask the OS for more memory or anything. We just reused an allocation that was made before. And that's the basic mechanism of the Tcache. So now on to the next kind of list that the allocator uses, that's fast bin. So fast bins store arbitrarily many small allocations. And that's an important distinction that I didn't actually demonstrate yet. So let me do that. Let me free some more chunks. So I'll free 3, and then 4, and then 5, and then 6, and then 7. OK, so 7 things all in the same Tcache list. If I say show me Tcache list 0, we got 7 pointers in here. So now let's free another thing. Let's free allocation 8. And now we can see this 8th freed allocation goes into a fast bin. So the Tcache bins are bounded in size. That bound is tunable, but by default 7. So you can see here, once we make our 8th, we free our 8th thing of the same size, we end up with that 8th one going into fast bin. And just to demonstrate here, if I were to make another allocation, one allocation of size 1, and then print the heap, you can see the allocation I get is actually the head of the Tcache bin. So even though the fast bin one was freed more recently, you go to the Tcache before going to the fast bin. And the reason for this is that the Tcache has no lock. So the fast bin is stored in the arena. It's stored in the main heap structure. So it's you need to acquire a lock before you can go look into the fast bin. The Tcache is per thread, so it's free to grab. It's fast. Tcache is optimized for performance. Fast bin too, but not to the same extent. OK, so let's talk about properties of the fast bin. So you can have as many things as you want in there, but they have to be small by default. Freed chunks that are small enough go to a fast bin when the Tcache is full. And it's just like the Tcache in the sense that, like, single linked lists, they all store chunks of the same size. So like each list stores chunks of one particular size, but of course each list has a different size for that list. And again, chunks are inserted at the head, so it's things reverse when you start thinking about repeated insertions and removals. Okay, so let's go a little bit further here. Let me rerun this. And first, I'm going to make, let's say, 15 allocations of size 1. So that'll get rounded up to 24. And we can see here are all our allocations, starting from 1 because 0 is reserved for the base chunk. And there's the heap. So now let's free these. Unfortunately, I don't have a good UI for freeing repeated chunks. If you think the UI is bad now, well, I'm going to have to run 15 2 commands to free all of those allocations I just made. And if I mess any of them up, then I'll get a double free and the whole program will crash. And I have just meshed one up. If I enter an invalid size, I can't remember if I have an error here. This might be recoverable. I might have to rerun the whole thing again. Yes, it's unrecoverable. OK, let's try this again. Allocate 15 chunks of size 1, free chunk 1, and then 2, and 3, and 4, and 5, and 6, and 7, and then 8, and 9, and 10. And let's look at the heap. So we can see 7 things in the Tcache and 3 things in the fast bin. Let's free 11 through 15. And look at the heap again. So now we can see the state of the heap here. There are 8 things in the fast bin, just to demonstrate that it doesn't really have a cap on its size. It's not like the Tcache where there's like a limit on the length of the list. OK, so now if I make an allocation of size 1, let's say just one of them, and I look where it came from, it's chunk 7, which came out of the Tcache. And that's just because the Tcache is the first place you look. Let's make 6 more allocations. And look again. Now the Tcache is empty, and the fast bin still has all that same stuff in it. And now we're going to get to a property of the fast bin I haven't yet mentioned, which is that if you allocate, let's say we allocate 1 chunk of size 1. And then we look at the structure of the heap now. Before I do this, does anyone have any guesses as to what might happen? So to reiterate here, what I'm doing is I have I had 8 chunks in the fast bin. I made 1 allocation. So 8 freed chunks that are like tracked in the fast bin list. I make a single allocation. What do you expect to happen? So maybe I have not given sufficient intuition for what goes on in the heap. But I'll clue you in. If you make a single allocation, well, certainly the allocation you get is going to come from a existing freed chunk. So here we got chunk 15, and that's this chunk here. So the most recently added chunk to the fast bin. But there's an optimization that happens too. And this is sort of the surprising thing, I think, which is that after making that allocation, the remaining chunks in the fast bin get opportunistically moved into the T-cache. And the idea here is if you're ever reaching into the fast bin, it means the T-cache is empty because you always go to the T-cache first. So if you're getting to the point where you're looking into the fast bin, like, must be the T-cache is empty. And if there's anything else in the fast bin, well, we're already grabbing one thing from the fast bin. Might as well grab them all and just move them into the T-cache, return, 1, and now the next 7 that are accessed will be faster. Further, if we look at the order of these things in the T-cache, you can see they're actually in forward order. So chunk 8 is first, and then chunk 9 and 10, etc. And that's not as you would expect because they were inserted into the fast bin list in, at the head, so the list would be reversed, but it gets reversed again when you move from the fast bin into the T-cache. When we do that opportunistic move, we're inserting into the T-cache at the head, so the list gets reversed back. So that's kind of, I would say that's sort of the T-cache and fast bin relationship is like T-cache is per thread, singly linked. So in that sense, similar to fast bin, but per thread and bounded in size. And fast bin is sort of like the T-cache, but no longer bounded in size and shared across many threads potentially. When you end up needing to go to the fast bin, it's because your T-cache is empty. So if there's more stuff to grab from the fast bin, you opportunistically move it to the T-cache. Okay. I feel like I may be losing people. So I think it's probably worth stopping for questions and maybe for re-explanation or something like that.
Well, I'll just say I followed everything so far, but I had no guess for that question because, like, I know enough C to know what you're talking about, but I've never been in this area.
Okay, very good.
Yeah, I wrote malloc a long time ago, back in PDP-11C.
Excellent.
Which never actually got to being released. They had DCC, and I wrote the whole libc in libc. Some I started with some of the DCS code, but mostly written in PDP-11 assembler or in C.
I didn't see Violet's question in the chat here, but why linked lists? I thought they were really slow. This is a good question. They are really slow, mostly. But yeah, I mean, Jerry's right that like they work well enough. The glibc malloc is like a big pile of code that has grown organically over a pretty long time. It started with DL malloc, which is sort of that was in like the 90s, maybe a little earlier, maybe the 80s. I'm not exactly sure. Before my time, but DL malloc is kind of a progenitor of many modern mallocs, and DL malloc was a pile of linked lists. So, you see that heritage today. Yeah, but there are certainly faster ways to do things, and other allocators make better choices with data structures. And glibc malloc is kind of, it's not trying to be the fastest malloc. It's not trying to be the universal, best in every capacity malloc. It's just trying to be like a good middle ground of all the things you want. It's not the most secure, but it's like good enough. It's not the fastest, but it's fast enough. And that's kind of the trade-off they're shooting for. If you're shooting to go faster than that, then there's definitely better strategies than linked lists. But like in general, it's like, fast enough. Okay, more types of bins. So small bins store like medium-sized allocations, bigger than what fits in a fast bin, but also the T-cache is full. So the small bin, stuff that fits in small bins could go in the T-cache by, in the default T-cache cap. But once the T-cache is full, you'll, go to a small bin instead of a T-cache bin. Small bins are doubly linked lists, and each one stores chunks of a particular size. And so now let's show what that looks like in Heap Explorer. So let's allocate like 10 chunks of size 200. Or, yeah, 200. And you can see these also, maybe I should have gone bigger, actually. Try this again. Let's say 10 chunks. Oops. Yeah, terrible UI. One more time. Allocate 10 chunks of size 400. Let's try that. And then look at the heap. Yeah. So I think this is big enough to end up in the small bin. We'll see. So if I free these chunks, so free 1, and then 2, and then 3, and hopefully I don't mess up typing here. And then look at the heap. We can see the first 7 end up in the T-cache like before, but now this 8th chunk ends up in a small bin. So a small bin is a different kind of bin. This is actually a doubly linked list, as I said a second ago, but more or less is like not too conceptually different from a fast bin. It's just doubly linked lists instead of singly linked lists. We'll get into the advantages and disadvantages of double linking and single linking in a few slides down the line. So on to the next kind of bin, that's large bins. So large bins are just like small bins. There's no cap on how many allocations they can store, but there is a cap on the size there. So if a chunk is too big for a small bin, it goes in a large bin. It can also be too big for a large bin, in which case it just gets M-mapped. So this bypasses the entire system. If you ask malloc for like a megabyte or something, it's not going to try to track it in the same way. It's not going to put it on the heap at all. It's just going to go M-map a megabyte for you and return a pointer to there. And then when you free it, it just M-unmaps it. Like past a certain point, having huge allocations just becomes a fragmentation problem. So it's not really worth thinking about. Of course, below a certain size, M-mapping every time is wasting a lot of space. So it's a trade-off. Now, large bins store a range of sizes. So unlike small bins that store one size, large bins store a whole lot of sizes. And they're sorted in an increasing order. So if you're walking a large bin, you want to know, like, okay, is there a chunk of size, 10,005? And you're in the large bin that spans the range from 9,500 to 10,500. And maybe there's, 1,000 allocations in the large bin of size 9,500. Then like you'd have to walk 1,000 links, which is going to be really slow. So there's a skip list in each large bin in which each chunk that is of a unique size participates once. So like the first chunk of each size participates in the skip list so that I can quickly walk down the whole list if I'm looking for a chunk of a particular size. Okay, so let's demo this. So first, I'm going to make some chunks. Let's say I'll make 10 again of size 0x 540, we'll say. And I'm just picking these numbers because I know that they worked when I practiced this a while ago. So like, I don't actually remember exactly what the limit is between what ends up in a small bin and what goes in a large bin. It's just not in my mind, not fresh in my mind. Okay, so if we print the heap, we've got sizes got rounded up a little bit, but more or less it's what we asked for. Let's now free a bunch of allocations and look at the heap again. And here we see something unexpected, and it's because I did my demo wrong. This is the unsorted bin, which we'll get to in one slide. But this is actually kind of a blessing in disguise because it lets me talk about something that I forgot to mention in the slides, which is chunk coalescing. So let me show a clearer demonstration of this concept. So we'll make 2 chunks of size, I don't know, 1,000, and show the heap. And then I'll make 1 chunk of size 1, and you'll see why in a moment. So first, I'm going to free chunk 1. And you can see here this ends up in Tcache. Now I'm going to free chunk 2. Oh, but it's in Tcache. I need to choose a number bigger than 1,000. Sorry. One more time. Allocate chunks. Let's do the number we did a second ago. We'll get 2 of them, and we'll make them 540. And then we will allocate 1 chunk of size 1, and here's the heap. So we've got base chunk, our 2 chunks we asked for, the chunk of size 1 that got rounded up to 24, hex 18, and then our top chunk. And now I'm going to free chunks 1 and 2. And look at the heap. And you can see there's just a single chunk here. So actually what happened is these 2 adjacent chunks that both got freed got squished together into 1 mega chunk. And the reason for this is that when you're trying to service a malloc, you can always cut a big chunk into smaller pieces to service small requests, but you can't always join small chunks into a bigger request, right? If somebody asks for a lot of memory, you might have to go to the top chunk, even though there's, the sum of all the freed chunks sizes adds up to more than what the user asked for. The memory needs to be contiguous. So it's advantageous to, join consecutive freed chunks when that happens. It turns out that chunks that are in fast bin and Tcache will never get joined in this way. But chunks in small bin and large bin and unsorted bin, as we'll see in a moment, can get joined in this way. If you free adjacent chunks and they end up outside of fast bin and Tcache, then they'll get coalesced before being added to whatever bin they belong in. Okay, so that's coalescing. Now let's talk about the large bin as I originally intended. So I'll allocate 1 chunk of size 540, and then 1 chunk of size 1 to prevent coalescing. And that was the point of this small allocation here, was that if I didn't have this allocation, then this coalesced, recall that this came from making 2 allocations of size 540. They get joined into 1 allocation of size A98. And that itself would be joined with the top chunk if I did not have another allocation in between to keep them separate. So that's the point of that little allocation. This is often called a guard, just a little allocation. Either it's in use or it's free but in Tcache or something that will prevent 2 chunks on either side from getting coalesced. Okay, so we print the arena. We've got a 548 and a 18. Now let's allocate another chunk, and it'll be another 548, and then another 18. So there's the heap. Now I'm going to free 1 and look at the heap again, and then free 3, and then make an allocation of size 600. And here we can see these 2 allocations end up in large bin number 68. We can look at that large bin by going to print a bin list and then typing in 68. And here you can see these are the 2 allocations in the large bin. The one that's green is first of its size, so it participates in the skip list, whereas this allocation here was freed second and has exactly the same size as this allocation, which was already in the large bin, so no need to put it in the skip list. The skip list is an optimization. It allows someone looping over the list to only visit chunks of unique sizes. So that's the meaning of the color here. Yeah, if let's say I make another allocation. So we'll print the arena. I'll make one more allocation, and I'll make it 560 big, and then make another allocation, a guard. Where? Oh, interesting. Oh, I was trying to make a guard after my 560. Instead, to make my guard, the allocator sliced off a part of one of the chunks in the large bin and then moved from the large. Okay, that's complicated. I don't really need to demonstrate this. The point is just that, like, if I had multiple sizes in the same large bin, then they would be stored in the order you'd expect. They're in sorted order, and the first of each size would be colored green. That's the point that I'm getting at, because that's in the skip list. Before I go on, I'd like to stop to ask for questions.
I was wondering if you've mentioned a heap several times, and does everybody understand what a heap is?
I would say a heap is the a part of memory that has stuff that didn't get allocated on the stack for a function call.
Pretty much.
Yeah,
That's partially correct.
A heap it's almost opposite of a stack. It grows from the bottom up or the top down. And that's where your uninitialized memory is allocated from, usually in a program. If it doesn't use Nmap.
Yeah.
So
the
historically, that's where all your malloc would come from, as a heap.
Yes. So, think local variables go in stack memory. Globals are statically allocated. They go in their own place. And then and static variables sort of in the same place. Then the heap is for everything else, basically. It's like if you have some, it's for dynamic memory. You don't know how much you need at the time. You don't know statically how much you need. You just request that much memory from the allocator at runtime.
There's a system called break, BRK, break and C break and stuff like that. And I don't want to get into that. Those go back to the very early days of Unix.
Yes, I had a slide about Burk and mmap and sburk, and I got rid of it because I didn't feel like making the diagram. But yeah, I mean, that's the way this works under the hood. Is you need to ask the OS for memory somehow, and Burk and mmap are how. Okay, so that's large bins. Basically, they store chunks of multiple sizes. They are sorted, and chunks of duplicate sizes, can occur. So if you want to just check chunks of unique sizes, there's a skip list that links together all the chunks of unique sizes. Okay, now onto the unsorted bin. The unsorted bin stores arbitrarily many arbitrary sized chunks. It's a doubly linked list. Because placing things in the large bin requires walking a skip list, so something that might be kind of slow. If you want to keep free as a fast operation, then assuming that the chunk that you're freeing can't go in fast bin or tcache or maybe a small bin, just kind of, instead of putting it into its correct large bin, just drop it in the unsorted bin, which is just one big long unsorted doubly linked list of chunks of whatever size. And then later when we malloc, if we end up needing to go to the unsorted bin because we've checked the fast bin and the tcache, or I guess tcache first, then maybe fast bin, and then maybe small bin, and then maybe large bin, and it's not in any of these places sufficient allocation that'll work for the malloc that the user wants, only then do we go to the unsorted bin. And while we're checking the unsorted bin, that's when we sort things into their appropriate places. So this is the effect we saw a moment ago in the large bin demonstration. And I can just try to make this a little bit just dropped a decent amount of equipment here, but I think that's probably fine. So just to demonstrate, so the heap's empty. Let's say I allocate, I don't know, 10 chunks of size. Never mind. Let's say I allocate one chunk of size 540, and then I allocate a chunk of size 1, and then a 560, and then 1, and then let's leave it at that. So, 4 allocations we made on the heap, 1 here, 1 there, and then these 2 guard allocations in between. So let's say I free chunk 1, and then I free chunk 3. Free chunk 3. And we look at the heap. Both are in the unsorted bin. And if we print out, oh, you know what? I may not have actually added functionality to print the unsorted bin. I can't remember. It might be bin 0. Let me just check. It is. Okay, great. So this is the unsorted bin. We can see that first on the unsorted bin is this more recently freed chunk, and then we have this one. Those are the 2 allocations sitting in the unsorted bin. Now, if let's say I free chunk, I don't know, 2, and look again, we'll notice that even though we have 3 free chunks in a row, they don't get coalesced because you can't coalesce with something in the Tcache. Because remember, the point of the Tcache is to avoid acquiring a lock. And in order to coalesce with stuff that's in the main arena, we would need to acquire a lock. So we don't coalesce here. Okay, so now if I make an allocation of size 1, let's say, well, I'm going to get the thing that I just freed that's in the Tcache, right? Because we always go to the Tcache first. But if I make another allocation, and let's say this one is size, I don't know, 600, bigger than we can support right now with either of these 2 on the heap in the unsorted bin, and then look at the heap, this is what happened. So we first, we are going to check the corresponding large bin for 600. And we're going to say, is there anything there? And no, there's nothing there big enough. So what happens then is we walk the unsorted bin, and we say, for each thing in the unsorted bin, is it big enough to fit an allocation of size hex 600? And the answer is no. I mean, we've got a 548, we've got a 568, and neither of those is big enough to do a 600. So what happens then is as we walk that list, we're going to take first, this should have been first in the unsorted bin, so this would get inserted first in the large bin. First, we encounter this chunk in the unsorted bin, not big enough to service our request. We're going to move it to a large bin. And then we encounter this chunk in the unsorted bin, also not big enough, so we're going to move it to its appropriate large bin. And then we've reached the end of the unsorted bin. There's nothing big enough to handle our request, so now we're just going to cut off some piece of the top chunk, and there's our allocation. So now just to hammer the point home, I'm going to print large bin 68, just so you can see here. There's 2 unique sizes, so 548 and 568, and I had it reversed. I could never remember. The 568 comes first because it's in reverse sorted order, so that's my mistake. The large bins are in reverse sorted order. Biggest first. Okay. Great. So that's the unsorted bin. That's all the types of bins. Now let's go into what the data actually looks like. So we've talked about how the data is organized. We've talked about how you free something, kind of where does this allocation end up? How is it tracked? But we haven't really talked about like the data structures here in terms of like, okay, what does the 5th byte of my allocated region actually mean once the chunk is freed? Great. So let's talk about chunks. the structure of a chunk. So when you make an allocation, this is the structure of the data that is given to you. So you get a pointer to here, sorry, to right here. This is where malloc returns, is this region here. But if you look just before that region, there's actually going to be an 8-byte field that you're not supposed to look at. It's undefined behavior to look at this stuff, but like if you want to understand allocator details, like you just have to accept the fact that everything you're doing is undefined behavior, and that's okay. So just before the data here, you have a field that I wrote down as size AMP, and sometimes you'll see this as like size or A or M or P in that way. And the point here is that the upper, this is a size T, so like on a normal 64-bit system, this is a 64-bit int. It's got the upper 61 bits describe the size of the chunk, and the size of the chunk is the size of the chunk overall. So imagine the data was empty. If that were possible, then the size would be 8. In fact, the data cannot be empty. So the minimum size of a chunk we saw earlier is 24. So the minimum size of this size here is 32, because the size itself takes up 8 bytes. Okay, then we have 3 bits of metadata. So if you might have noticed that like every single chunk size we saw ended in an 8. It's also possible to have chunk sizes that end in 0, but that's it. You're not going to see chunk sizes. Chunk sizes are always going to be a multiple of 8. What that means is that the low 3 bits of the chunk size are wasted. They're always going to be 0. If you just stored the size here, well, then you'd always have 3 zeros on the end, because the size is always a multiple of 8. So that's a waste of space. And so they reuse those 3 low bits for storing basically like 3 Boolean values. So the first of these is whether the chunk is in an arena other than the main arena. And basically this only comes up in multi-threaded scenarios, so we won't really discuss it. But the point is just like, this will be 1 if you got this chunk in a thread other than the main thread, more or less. So this is like bit 2, the third lowest significance bit is that. But so this is almost always 0 for like simple single-threaded programs. The next lowest significant bit is M. So that's whether the chunk is M mapped. And that's pretty straightforward. If the chunk was big enough that it was going to get M mapped, then when you pass it to free has to have some quick way of deciding, do I M unmap this thing, or do I put it in a bin of some kind? And the way it knows is just by looking at this bit. And then the lowest bit is P, and this one's kind of weird. You might have noticed that, well, I guess I haven't shown you enough information to notice this, but there's actually no way, there is no piece of metadata you'd imagine like inside of a heap chunk you might store whether the chunk is free or not. That's in fact not what is done. What's done is a little bit weirder, is you have this P bit for prev in use. And what this is saying is the chunk just before this one, contiguously in memory, is that free or not? If this is 1, that means that chunk, if this is 0, that means that chunk is free. If this is 1, that means either that chunk is not free or it's in fast bin or Tcache. So basically, if it's 0, if the low bit of a particular size is 0, it tells you the previous chunk in memory is free. If it's 1, it tells you, well, maybe it's free, maybe it's not free. But you can't really, you're not certain, basically. It could be in Tcache or fastbin, meaning it's free, or it could be in use, and this bit doesn't really tell you any more information about that. And the reason you need this bit is that if you look at the glibc malloc struct for a malloc chunk, it looks a little bit different from this. I'll go bring it over here just so we can talk about this distinction. So struct malloc chunk looks like this. You can see the very first thing in the struct is this prev size, which is a size t. And this is kind of a weird thing, is that the glibc malloc struct kind of overlaps with the logical chunks. So the idea is that, like, where I'm representing a chunk as beginning here, glibc considers a chunk to begin 8 bytes earlier. But this field is only valid if the previous chunk is free. So if the previous chunk is free, then this field here, this 8 bytes that would come just before this size of the current chunk, would describe the size of the previous chunk. And you can use this for backward coalescing. But if the previous chunk is not free, then just don't look at those 8 bytes. That's the rule. Okay, so on to what a chunk looks like in the Tcache. So this is what an allocated chunk looks like. You know, what you see, what comes out of malloc is just this, which could be anything. But if you look 8 bytes before, you'll find a size with 3 bits of metadata. And if you look 8 bytes before that, if the previous chunk is free, you'll see the size of that chunk. Okay, in the Tcache, things look a little different. So you can see immediately, like, okay, the size is the same. This is actually the same for all of the different kinds of chunks. But after that, memory starts being reused. Because, of course, in a freed chunk, we don't actually care about the data. The data is, that was the user's thing to think about. Now that they've freed this chunk up, we're, you know, perfectly free to reuse the space there for our own purposes in the allocator. And because the minimum chunk size is 24, we've got 3 words. And I'm thinking 64-bit systems, so, you know, on 32-bit or lower, you know, this is maybe different. We got 3 words of space to work with. So in a Tcache chunk, we use 2 of those words. And one of them is for the forward link of the linked list, because, you know, Tcache singly linked list, so got to store that link somewhere. It goes right here. And the other one is for something called the Tcache key. And this is kind of a weird thing. It's a per process random number that gets written into every Tcache chunk when it gets freed. So inside of free, if your chunk is going to go into the Tcache, we go and write this special random number at offset 8 into the chunk data. And the point of this random number is to detect double frees. So, you know, you might think you could actually, in principle, do a lot more with this random number. I think there's probably, this is an underutilized thing in the allocator. But what it's actually used for is, like, if you free a chunk that would otherwise go in the Tcache, it's like small enough, and it has this random number at this offset already there, then very likely the reason why that's already there is that this is a double free. And then so then at that point you walk all of the free lists and you check, hey, is this thing in my Tcache? Yes or no. And if it's in the Tcache, well then, you know, abort with some error saying double free. So if you ever see, like, if you double free a reasonably small allocation, you'll very likely get an error that says, like, you know, double free detected parentheses Tcache or something like this in a modern glibc. And this is why. It's because you've got this random number here. If it finds that random number in an allocation, you know, being passed to free, then it's going to check, is this allocation actually already being tracked in a free list somewhere? And if so, then crash. Okay, so that's the Tcache key, or also known as the Tcache cookie. I submitted a patch related to this that was denied for performance regions, and I'll go into it if anyone's curious. But I'm going to move on for now. Okay, next we have what a fast bin chunk looks like. So a fast bin chunk looks basically the same as a Tcache chunk, except you don't have that key anymore. There's another thing I've sort of skipped over here, which is the meaning of this word swizzled. This is also known as safe linking. This idea, basically the principle is that instead of storing a pointer, like just an address in this spot, we actually store that address XORed with the address of the address shifted right by the page shift, so 12. And basically the idea here is, like, suppose an attacker gets the ability to overwrite one of these pointers, then they can do some interesting stuff that we'll talk about in a little while. And if that's the case, then if the pointer is stored XORed with some function of its own address, then they also need to be able to break ASLR in order to overwrite this pointer and have everything work out. And for those who are unfamiliar, ASLR is address space layout randomization. That's basically every time you run a program, things are going to be in different places in the address space. So sometimes it can be pretty difficult just to know, like, what is a heap address? Like, give me an address on the heap. If ASLR is turned off, then it'll be fixed every time you run the program. You know, the heap will end up in the same spot. If ASLR is turned on, then just figuring out a heap address can be kind of difficult. So even if you have some kind of exploitable bug that, you know, would maybe allow you to, like, you know, leak some data off of the heap that's supposed to be secret. Well, if you don't know the address of that data, maybe you can't use that bug. So that's the principle here, is that we should make a use after free in which you would control this pointer here as an attacker slightly more difficult to exploit by requiring that the attacker also know the address of this field here, and you know, therefore have broken ASLR. Before I move on, any questions about this? Okay. Onward. Great. So that's what we mean by pointer swizzling. You'll see inside of glibc, this is called protect PTR, also known as safe linking. So it goes by many names, but it's relatively straightforward. It's take the pointer, XOR it with some function of its own address, which is usually shift right by the page shift. Okay. Now here's what a small bin chunk looks like. It's the same again in the beginning, right? The same size, and then the AM and P bits. And now we have a forward link and a backward link. So as you'd expect, it's just a doubly linked list. It's the same as a fast bin chunk, but now we have a back pointer too. So that's pretty straightforward. Unsorted bin and small bin look the same. And then we finally have the large bin, where we need to have the skip links in addition to the regular forward and back links. So the skip links are kind of, you know, what you'd think. They're just pointers that go to the next chunk. For those chunks that don't participate in the skip list because there's other chunks of the same size, then these are just both going to be null. And in fact, I believe they have to be null. It's not like they won't be looked at. It's like you can determine whether a chunk does participate in the skip list by looking at whether these two pointers are null. Don't quote me on that, though. Okay, on to attacks. So what can we actually do with a heap use after free, or you know, a heap buffer overflow or whatnot? So we're going to begin with kind of the simplest type of heap exploit. This is known as an unlinking attack. So an unlinking attack is really not specific to heaps. It's just a doubly linked list problem. And it really comes up from a pretty fundamental fact of doubly linked lists. So we'll open up this C program here, and I'm just going to, maybe I should send it to you all instead of having you read it off the slide. That's probably not the most effective way to do it. So let me just, if I could paste this in the chat or a paste bin or something, that's probably the right way to do it. So let me go make a paste bin, and I'll send you all this C code here. Great. And I'm going to remove the bottom. I'm going to remove a few lines of code from the bottom of this paste here, just because there's a part of this I don't want you to see yet. Okay, and one more time after proving that I'm a human being. Great. So here's the paste. Let me send this to you now. Cool. So at that link, I've got some C code. And I'll also have it on the screen here. So this is just a a doubly linked list. There's nothing complicated here. This is your intro C class. It's going to cover this material, but just to, in the interest of being thorough, we've got a node struct with a pointer to a prev, a next, and then char star data. We've got this die function, which is just write an error to std error and then exit failure. And then we have 4 list operations. So the first is new, which takes some data to put in the first node of the list. It's going to malloc a node, and malloc, do the error checking on malloc, and set prev and next to be null, set the data to be the data you passed in, and then return the node. Then we have an insert after, which you give it some node in the list, and then some data to put in the new node. It'll make a new node. It'll put that new node just after this node in the list, and link things up appropriately. And then lastly, we have list remove, which is just an unlink from the list followed by a free. So you pass it the address of some node, and it's going to take it out of the list. Okay, so then I have list remove safe here, which is sort of should say something about list remove. So we'll get into that in a moment. Then I've got a static char here called authenticated, which you might anticipate is something that it's in our interest to change to a non-zero value. Okay, so here's main. Main is first going to make a list node, make the first node in the list, and then insert after the first node, the second node, and then insert after the second node, a third node. And now we're going to begin the portion of the program that corresponds to the hypothetical vulnerability. So here I'm leaking the address of authenticated of this variable, and the assumption is that the attacker knows this address. Either maybe it's a statically compiled program, so there's no ASLR. We're just going to pretend for a moment that I know the address of this thing I want to overwrite. As an attacker, I want to change this variable from 0 to non-zero so that later I can get this put s to tell me that I win. That's what I live for. So here's our leak. We're going to just print out the address of that variable. And then I've got a buffer here where we're just going to read into it some bytes from stdin, parse them as an int, and overwrite the second node's forward link, and then it's backlink, and then it's forward link after reading from stdin again. So the idea here is that this corresponds to a use after free, because recall that the chunk data and the chunk metadata overlap in freed chunks. So if we have let's say a large bin chunk, like this right here, when the chunk is allocated, is part of the data of the chunk. So if you have a use after free, you get the ability to write into these fields potentially. And that's the thing I'm sort of simulating here by just reading from stdin into a linked list node's pointers. Okay, so then we're going to remove this second node from the list. So we're going to unlink it. And finally, if we are authenticated after that, if somehow this unlinking process changed this variable from 0 to 1 or 0 to anything else, then we win. And you can just ignore the memory leak in this program, or the memory leaks. Okay, so obviously, given that I've named a function here list remove safe, it kind of implies something about list remove. I guess the question is you have control of the forward and back pointers in second node. You can make them whatever you want, and you know the address of this variable, of this thing in memory that you want to change. How might you use this unlinking routine that gets called on second node just after you change those values to overwrite this variable with some value that you want? I'll leave that as a question for the audience. Oh yeah, pastebin is now terrible. You need an ad blocker on there. I'm going to put the screen back onto the code and give you a moment to think. Any takers? All right, I'll spill it. So the principle here is that basically to unlink something from a linked list, an unlink is pretty much just two writes. And if you control what the pointers are of the linked list node that you care to, that's getting unlinked, then you control the value being written and the destination of the write. So let me draw this out, and hopefully it should make somewhat more sense. So let's say we have like a linked list with like 3 nodes, as we had in that demonstration. Hey, it recognized the rectangle. Great, so here's our linked list. This is like, node 1, node 2, and node 3. Okay, and suppose we gain the ability to overwrite the pointers in node 2. So that means we get the capability to overwrite this arrow to go wherever we want. We can also overwrite this arrow to go wherever we want. And now suppose down here is this magic thing we want to control, authenticated, down here. Okay, so what we could do is we could basically say, let's think about just what unlinking actually means. To unlink something from a linked list means we're going to take this guy. This is passed into our unlinking function, this N2. And we're going to first follow its back pointer, and then change the forward pointer of the node we arrive at by following the back pointer to go to N3. So we're basically going to say, actually, like, let's delete this arrow. We'll throw that away. And when we unlink, we're going to point this over to here. But why N3 in particular? Because the forward pointer of N2 goes to N3. Okay. And then correspondingly, we're going to follow the forward pointer of N2 to arrive at N3. And take N3's back pointer and change that to go back to N1. So that's what it means to unlink. And of course, you might also consider deleting the back and forward pointers out of N2 to avoid, weird dangling pointers. Although this is probably going to be freed, immediately after. Okay, so that's a normal unlink. Now, if we think about what if we control these back and forward pointers, this pointer here, and this pointer here, sorry, this pointer here, we control, and we also control this one as well. Those are the 2 pointers that we control. Then we actually control both the destination of the write and the value that is written into that place. So if we look at the code, you can see we're saying, so if node arrow prev is like not null, well, then node arrow prev arrow next is going to be node arrow next. So recall, we control node arrow prev and node arrow next. We're reading those straight out of stdin. So basically what we're saying is like node arrow prev, something we control, arrow next, meaning +8, plus size of struct node star, like equals node arrow next, something we control. And then node arrow next arrow prev, meaning node arrow next, something we control, arrow prev plus 0, because prev is the, the first field in the struct, equals node arrow prev, something we control. So it's just saying like, write into a destination you control, a value you control, and then also do the inverse of this, right into that value, the destination. So the restriction on what this value you get to write is that it has to be a valid address, or else you're going to segfault in one of these two lines. But the capability here is that you can, if I say I run make and I run unlinking attack, it tells me, okay, authenticated is at this address. Well, all I have to do is say, let's write at that address. And oops, sorry, that's the safe version. I forgot to change the code. I need to use the unsafe version. Let me find. Yes, this should be list remove, not list remove safe. That's supposed to come next. Okay, so if I here we can see authenticated is at this address. This is actually different from last time because of ASLR. So we'll say right at that address, and we have a segmentation fault. This is my fault. I need to compile statically. Sorry. With these demos, it's always a mixed bag. Okay, put there, and now we can see we win. So the idea, just to really drive the point home, is we're saying here point N2's forward and back pointers add authenticated, and technically, like it, the forward pointer I believe should be at authenticated minus a little bit. But if we point these two here, then when we unlink N2, we're going to say go to this spot and write into it the value of N2 arrow next, which is also this spot. So we're basically going to overwrite authenticated with the address of authenticated. There we go, of authenticated. This is some terrible handwriting. But the point is we're overwriting this value in memory with its own address, which is, of course, going to be big. And very likely the low byte of that is going to be non-zero. So we get that our char is non-zero. So that's the thing we want. And that's why we get this put SU in. Authenticated has been overwritten with the address of authenticated, which is what we want. In fact, we can overwrite authenticated with any valid address. And there are valid addresses with low byte, whatever we want. So we can overwrite authenticated with an arbitrary byte value. So that's an unlinking attack. And in the past, like DL malloc was vulnerable to this kind of thing. If you had use after free, you could basically use it to gain more or less arbitrary write into, write whatever value you want into whatever part of the address space. And this was useful. And then came a mitigation. And this is an extremely effective mitigation. Every linked list based heap uses this mitigation. So any ideas what that might be? If you're trying to combat people overwriting links in your linked list, what might you do to stop this? Let's I can pull up the picture even. So this is the kind of situation you're trying to avoid. So in the interest of time, maybe I should just give the answer on this one as well. The idea here is that this does not look like a normal linked list. This is a very weird looking, this is not really a linked list. And crucially, the property of a doubly linked list that's missing here is that there exist points in the list where you can follow a back pointer and then follow a corresponding forward pointer. Like if you think of this thing as a struct node star, like, you know, it's got a forward pointer that goes somewhere. Maybe it's like zeros just after this thing, or maybe it's not, or maybe it goes to some address, or like, who knows? It's just whatever's in memory. But crucially, there's not going to be, at the place you want to overwrite, that does not contain your own address. Like there's no such arrow as the one I'm drawing right here. Like this is not real. And that's the property that you can use. You can say, okay, I would expect basically at all times in a linked list, if I take, you know, assuming that it's like consistent, if I take the forward pointer of any node and I follow it, and then I follow the back pointer, whoa, then I end up back where I started. And if I follow the back pointer of any node and I follow the forward pointer of the node I arrive at, then I also end up back where I started. And that's kind of a key property of a doubly linked list. Like, of course, you'd want it to be that the forward and back pointers are like inverses of each other. Following any node, arrow back, arrow forward, and arrow forward, arrow back should both be the identity. So this is, of course, broken when you have a situation like this. You no longer have that property, and it's very easy to check that property, right? You just follow the pointer and then follow it back. So that's exactly what glibc does. Basically all over the place, like they have, anytime you're going to unlink something, you first check, if you're unlinking from a doubly linked list, you first check, hey, if I follow this pointer and then I follow the corresponding back pointer, do I end up back where I started? And if we add in that mitigation, it's pretty simple to implement. We're just saying, okay, if the prev is not null and, you know, following the prev and then following the next of that thing doesn't get me back where I started, or the corresponding case on the other side, then like the list is inconsistent, so just crash. And only if, you know, this check passes do we actually go and remove the node from the list. And as you saw earlier, before I foolishly forgot to edit my code, we can see here in this list remove, if I change this to list remove safe, which actually does the link checking, then you know, I can try to run the same attack again, but it won't work. It'll detect that the list is inconsistent and it won't print out that I win. So that's the kind of the simplest unlinking attack. This is obsolete and has been for a long time. This consistency checking is really standard in most places. But it turns out that actually there are some places, there's a few places in glibc where the consistency check is missing. And as far as I can tell, it's just an oversight. And it turns out these locations are pretty well known, but just not to the glibc maintainers. So like if you look, the Arizona State CTF team, Shellfish, which started at UCSB and is kind of a multi-university collaboration, they maintain this repo how to heap. And in how to heap, they document a bunch of techniques for messing with heap metadata. And most of these are not original and are from other places. But a few of them, I believe, are from how to heap. I'm not exactly sure. But these are basically like oversights in glibc, many of them. And one in particular that stuck out was this, where is it? Here, large bin attack. This is basically exploiting a missing linked list consistency check in the large bin. So I can show you how this works, and then I can show you what the fix is. So let me first run Heap Explorer. I haven't actually tested these demos on the version of glibc that this system runs natively, so I'm just going to run these in Docker containers to ensure that things go according to plan. Cool. Throw that over there. And then Docker exec into the container. Okay. So here's a large bin attack. Oops. I guess cat large bin attack. So the idea is really straightforward. First, we have this authenticated variable, just like we had before in the the contrived unlinking attack. This is like a real-ish version of the same idea. So first we malloc a chunk of size 560, and then a guard chunk, and then a 540. and then a guard chunk. So we're setting up 2 chunks to end up in a large bin. So we free, and that's going to place the 560 into the unsorted bin. Then we malloc 600, where we're going to have to walk all of the bins and find that there's no chunk of sufficient size. But in doing so, we'll sort the 560 into the large bin from the unsorted bin. Then we'll free P2, which will place 540 into the unsorted bin. And then we will do an overwrite of P1's back next size. And this is exploiting the missing linked list consistency check. But really, the place this would come up again would be if we had a use after free. I can make this bigger. So if we had a use after free, we might have the capability to overwrite this pointer. And then supposing we malloc another 600, well, we won't find that on the unsorted bin, but we'll sort the 540 into the large bin. And when we place that 540 into the large bin, that is when this unlinking attack occurs, more or less. It's a little bit different from the demo I gave a second ago, but the idea is basically we're going to follow this back next size pointer, and in doing that, we will end up overwriting authenticated. So let me show how this works in a little bit more detail. Let me take this and throw it over here, and then make this bigger. Okay, so I'm just going to make the same sequence of allocations that this program does. So first, we're going to allocate 1 chunk of size 560, and then 111, and then 540, and then 11. Oh, dang. I already messed up. Let me try this again. Okay, make an allocation of, it's one of them, and it's size 560. Make 1 allocation of size 1, 1 allocation of size 540, and then 1 allocation of size 1. Okay, so here's the state of the heap at this point. We've got our 560, our 24, our 540, and our 24. And, you know, technically 568 and 548, but that's like fine. Great. Now we'll free that first allocation. So we will free 1. And look where it ends up. It ends up in the unsorted bin, as you would expect. Then we malloc 1 chunk of size 600, which is going to cause our allocation from a moment ago to get moved from the unsorted bin to the large bin, because when we go to make that 600 allocation, we walk the unsorted bin looking for something big enough. We don't find it, but along the way, we sort the things that we do find. So if we look again, now this is in large bin 68. Okay. And at this point, so this is the state of the heap at the point when the back next size pointer of this chunk gets overwritten. So I could try live attaching to GDB and running this in Heap Explorer, and we could see if, honestly, that sounds like it won't work. I feel like I'll mess that up. So instead, I'll just run this demo program directly. Okay, so here is the demo program. And if I run this large bin attack demo, then it says I'm in. Now, of course, that's not very interesting if you don't know what the program does. But the idea here is we're overwriting this back next size pointer with the address of authenticated minus 32. And this is because 32, if we go all the way back to the structure of the chunks, back next size is at offset 32 into the chunk data. So that's where the 32 comes from. Okay, so we overwrite we take the address of authenticated minus 32, and we write that into P1 in its back next size field. And then we make an allocation, which is going to cause this 540 sized allocation to be placed into the large bin, because right now it's in the unsorted bin. Sorry, I forgot to free 3. So this is the state of the heap at the point when we do our use after free overwrite. So we have 1 thing in the unsorted bin, 1 thing in the large bin, and there was a missing check for linked list consistency when we move something from the unsorted bin into the large bin, if that thing that's getting moved is the smallest thing in that large bin. And that causes, it gives us, you know, this ability to write a heap address at an arbitrary location. And that can be useful. Heap addresses are big numbers, and you can use them to overwrite interesting stuff. You can also use it to bypass ASLR for the heap. So maybe you've broken ASLR for something, but you don't have a heap address yet. Well, you can use this kind of technique to obtain a heap address given a use after free. A use after free that's only a write, let's say. So that's kind of a potentially useful technique, but it's kind of just an oversight in terms of like where the consistency checks are. So the fix is pretty straightforward. I can pull that up here. This is a patch we submitted a while ago. Let me try to find, got it somewhere. Here we go. Yes, so here is the patch. This was merged and released in glibc 242, which is new enough that probably none of us have it on our systems. It's like in the last month or so. Okay, so basically the patch is just, I can pull up the glibc source code, but the patch is just this. It's a 2-line check. It's just, hey, if basically following back next size arrow forward next size does not bring you back where you started, then your large bin is corrupted in the skip list, in the next size pointers. So you should, fail. That's it. Pretty straightforward. The larger context here is actually kind of worth taking a look at. Here in malloc, malloc.c is big. It's 6,100 lines. Could be worse, but could definitely be better. And this part, I think, is among the most confusing parts of the file, where it's just like forward arrow, back next size, arrow forward next size, not equal forward arrow forward, is a hard statement to parse. Forward equals back equals back arrow back. It's not very readable code. And it, honestly, coming up with the right expression here took me longer than I would like to admit. Yeah, so this is, if anyone's interested in doing a refactor and in puzzling with some annoying linked list code, I'd say this is a good candidate. Okay, so that's the large bin attack. No longer works because of a really simple patch that we made. And it's basically an unlinking attack. Okay, now onto the final attack I'm going to talk about. It looks like I have just barely enough time to maybe mention this. So that's the reverse into Tcache. And this is a technique that is also documented in How to Heap. So really highly recommend checking out that repo. How to Heap has a lot of really good stuff. So here is reverse into Tcache. Basically, the principle, I unfortunately don't have a reverse into Tcache demo that I wrote anymore. I couldn't really find it when I was putting together the slides here. I've done it before, but I have a variant that I wrote that actually still works even with the mitigation. So we'll just use that one to explain the concept. So recall that when you recall that when you allocate more things than fit in the Tcache, like once the Tcache is empty, you reach into the fast bin, and if you reach into the fast bin, you're also going to move stuff from the fast bin back to the Tcache, and in doing so, reverse the order of the stuff in the fast bin. So it's like, the simplest case is I say, give me like 15 chunks that are all size 1, and now free all of them. Okay, they're all free. And 7 in the Tcache, 8 in the fast bin. Now start allocating chunks. Let's say we allocate 7 chunks of size 1. Now the Tcache is empty. The fast bin still has 8 things in it. And as soon as I allocate 1 more chunk, and I look again, now the remaining 7 chunks, these 7, get moved from the fast bin back into the, into the Tcache because it's faster. So that like little land grab that this thread makes out of the global shared fast bin is the thing we're talking about exploiting here. So this is honestly, if the last one was complicated, this one is maybe a little more complicated. So I do have a diagram. So this is the idea. So we first make 15 allocations to fill the Tcache, and then free them all to fill the Tcache and put a bunch of things in the fast bin. Then we clear out the Tcache by making 7 more allocations. So this is exactly as we just did inside of Heap Explorer a moment ago. So at this point, the Tcache is empty and the fast bin has 8 things in it. And then we change this pointer to point to wherever we want. So maybe the goal of this attack is like we have use after free and we want to control like some stack variable or something. Well, you could just change this pointer to anything you want it to be. And in this case, I'm pointing it back into the list, but this is just a detail. You could change P7's next to go wherever you want. And before our mitigation, then clear out the Tcache again, and you'll end up with basically P7 will be in, P7's next will be in the fast bin leftover. And that's the point. It's just that like by changing P7's next in this context, if it's like kind of on the end of the fast bin, when we move stuff from fast bin to Tcache, we can't really check consistency on this linked list. There's a few workarounds you can kind of do, but it's a singly linked list. So there's no way to follow a back pointer after following a forward pointer. So it kind of has to trust you on this. So if the forward pointer says that it goes somewhere, it's just going to move from the fast bin into the Tcache wherever that forward pointer goes. You can't do exactly the same attack on the Tcache because the lengths of the Tcache lists are stored separate from the lists themselves. So if the length doesn't match up, then it doesn't work out exactly right. You could do it on like the second to last element in the Tcache, but that leaks a little bit of memory, which maybe matters. Okay, so the point here is basically if you change the next pointer of P7, you can make it go wherever you want, and that can make an arbitrary address be returned from malloc, which might give you control of memory you don't already control. So the mitigation here is pretty straightforward again. The idea is basically similar to a linked list consistency check, right? We can't just check that the back pointer goes where we started because there's no more back pointers in a single linked list. But we can check that the rest of the metadata kind of looks right. So for example, fast bins store chunks of a particular size. So if we find a fast bin link that points to an address that doesn't have the right size field at the right offset, well, that tells us something. That tells us that probably this is, someone's trying to mess with our fast bins. So we should reject. And again, here the patch is very, very straightforward. It's basically saying, figure out which bin we would expect this thing that we're moving from the fast bin into the Tcache, figure out which Tcache bin you'd expect it to go in. And hey, if it's not the one that we've been moving stuff into, if it's not the one that corresponds with this fast bin, then we have a chunk size mismatch. So we should die. That's the whole patch. That's the whole point. Now the workaround for the patch is you can turn use after free into double free, which is maybe sometimes useful. And the way you would do this is by taking P7's forward link and pointing it back into the list into P13 here. So the idea is, recall, we start with 15 allocations. We free them all. So now Tcache has 7 and fastbin has 8. We clear out the Tcache. So now the Tcache is empty and fastbin still has the same 8. Then we change P7's forward link, which right now is null, and we point it back to P14. I'm sorry, to P13. And then make a single allocation. What happens next is first P14 gets returned. So, or marked for, to be returned. P14 is like removed from the list so that it can be returned to the user. But before it gets returned, we're also going to opportunistically move from the Tcache from the fastbin into the Tcache. So first we'll take P13 and move that into Tcache. So we're going to kind of, in a sense, we're unlinking it. We're taking the head of the fastbin. Now it points to P12 and taking P13 and moving it into Tcache, and then setting its next pointer to be like null. And then we do the next thing, the same thing to P12 and P11, 10, 9, 8, 7. And so we end up, back in forward order with 7, 8, 9, 10, 11, 12, 13 in the Tcache. But because 7's forward pointer points to 13, and 13 being a valid chunk in the fast bin does contain the correct size, this bypasses the mitigation that we submitted. So even on glibc 242, in 10 years when you all get that release, you can still do this technique, which is kind of sort of related to the old technique, which will allow you to then have 2 copies of the same chunk on 2 different free lists. And then you have memory, pointers aliasing each other that shouldn't. And this is also a useful primitive to do stuff. So I could run this demo, and at the end you'd find that poisoned 1 does equal poisoned 2. We get 2 subsequent mallocs that actually return the same address with no intervening free. And that's the thing that we get out of all of this work. So if we run this here, and then look at the return value, it's 0, indicating that indeed these 2 pointers were equal, and so 2 subsequent calls to malloc gave the same value. So yeah, that's the last technique I wanted to cover. I do have a couple more I could talk about, but it's already 9. And I think I've probably worn you down with this much glibc heap. So if anyone's curious, I could go into one more technique, but otherwise I'm happy to end it here.
No, I'm fine with going on a little further.
Okay. Okay, so the last thing I guess I'll mention here is interesting ways to repurpose this guy, this key here, this random number that's placed into the Tcache chunks. So like when I first saw this, I was like, oh, random number placed in every chunk, kind of right in the middle of data that might be overwritten by an attacker, who has a use after free. That sounds like maybe like a heap equivalent of a stack canary. That sounds like something that could be used to detect a use after free. But instead it's used to detect a double free, right? The use is if you see this number at this position in a chunk that's passed to free, then walk the Tcache and make sure that it's not already there. And if it's in the Tcache, then that's a double free. So that struck me as a little weird. Like it seemed like there was some missing utility here for that Tcache key. Further, Tcache is per thread. So what this means is that if you free a chunk in one thread and then free that same chunk in another thread, well, you won't catch the double free because you won't walk the other thread's Tcaches, you just walk yours. So like not only does this not do, it doesn't detect use after free, the current mechanism, it also doesn't detect double free across threads. And so what I had proposed was a change to malloc that was rejected for adding 9 instructions to malloc, which, the glibc people certainly care about performance, so I don't blame them for this. But I do think it was a good change. The idea was basically at malloc time, make sure that if you're mallocing something, if you're pulling something from the Tcache, well, make sure that this key hasn't changed. Make sure that this is what you expect it to be. Because if it's changed for one of 2 reasons. Either you have use after free, so somebody is writing into this chunk after it was freed and they overwrote the key. That's one possibility. Or you have double free because across threads. So some other thread, freed this chunk and therefore overwrote the key with the key, so it stayed the same. But then later that, some thread mallocked and malloc returned this chunk. And when malloc pulls a chunk out of the Tcache, it overwrites the key with 0. So that means the second time, if a double free caused this chunk to end up on 2 free lists, which is what would happen if you had a cross-thread double free, then the first malloc would succeed and work fine. It would overwrite the key with 0. But the second malloc would be able to notice, hey, wait, this key is 0 now. It should be this big random number that I know, it's stored in a global somewhere. So doesn't compare equal, doesn't check out, and that should crash the program. So this allows you to detect cross-thread double freeze, not at the point of the double free, but at the point of the corresponding malloc to the second free. Unfortunately, this wasn't merged, so that's a little bit of a shame. I would say the other useful place you could use this key would be, and probably the more impactful place is for detecting just normal use after free. So not even considering double free here. Just like if you wrote into this is the chunk data starting here. So if you had a use after free that just like is a straight linear buffer overflow, like starting from here or something like that, like it's just a straight write, you'd have to overwrite the key, which means that you need to learn what this is. You need to somehow leak this random value that might not be the easiest to obtain. So that was my denied mitigation. And that's where my material is. So thank you all for listening. Happy to take any questions. Obviously, I got kind of fixated on the glibc heap. My knowledge isn't quite as sharp as it used to be, but I think I'm still not too bad, and happy to answer any questions you all might have.
Hey, Ben, thank you very much.
Yeah, thanks, Ben.
Sure.
I don't have any questions, but I just want to say thank you very much for that talk, because I'm not like, I've never done real serious C work, but it's the foundation of everything. And in my mind, glibc malloc has always just been this black box, like here be dragons, you're not meant to understand it. And I feel like I understand how it works and how it does what it's supposed to do without eating the CPU cycles. And I thank you for that. I feel enlightened.
Very good. Yeah, unfortunately, I feel like the more I learn about it, the more I still feel there are dragons. But yeah, definitely the initial wave of dragons has been repelled.
Yeah, I remember digging into all this stuff. I think it was in 1985 the last time I did it. So that's 40 years now.
I was -14.
Yeah, I did that. I'm just trying to remember my times when I was, my first digital contract was to write PDP-11C.
So I taught a systems programming course that was very small. It was only 5 students, and the not quite final project was to write a malloc, and I pretty much gave some form of this kind of talk to the students, and then said, like, go forth and write the interesting malloc of that you dream up. It doesn't have to look like glibcs at all. Yeah, no, unsurprisingly, everyone converged except for one student, basically on exactly the glibc design of pile of linked lists. There's something appealing about this, and a minimal kind of pared down version of this sort of thing. You can do it in like 300 lines.
Yeah, because a lot of the other standard database type structures don't really work well for malloc.
Mm-hmm.
It's like
I think
for any type thing you have to do in programming, is the data structures are really the key to it.
Yeah. The only student who did not do glibc style or DL malloc style malloc wrote like a slab allocator. So basically, you have a whole bunch of separate M-mapped regions that are, and each one stores chunks of exactly the same size. So now you don't need any more to store, like, you no longer need to store as much metadata in line, because you know where each chunk begins and ends just because they're all the same size based on their location.
When I wrote
simpler design in some ways, and
when I
more
wrote the
complicated.
malloc, PDP-11C did not have virtual memory, so it was a different animal back then. You had real memory addresses.
This is for what was the rest of the? So what was the OS here, if any?
I had to write the C runtime libraries for Ristus. There were 3 operating systems that essentially PDP-11C ran on. RT11, Ristus, and there was one other. They were all very similar.
But I assume you don't get a ton of support from the OS here in writing something like malloc.
No.
Okay, yeah.
Yeah, again, you had to understand the structure of programs. You know, I was going to write structured program. You know, you have your BSS section. You have your code section. And when you're talking about virtual memory, it's important to know where those are and how those are allocated. And when I wrote the assembler for Digital Unix, yeah, I had a lot of trouble because some things in memory weren't documented. And your addresses had to go through a translation.